Swayam Prabha. Digital India. Educated India.
So, in the last few classes, I've been talking about various biopolymers. We talked about cellulose, okay, which is most abundantly available polymers in the natural, in nature, and we saw how cellulose can be sourced from various agricultural materials. So, second, then we talked about starch, okay, thermoplastic starch, again based on cereals, grains, and various other agricultural products. So, now we will go to slightly a different kind of biopolymers which are not available naturally, okay, that you can extract like cellulose or TPS, but rather you can extract some monomeric molecules and then use them to polymerize it, okay. So, in that context we are going to talk about this polylactic acid, in short PLA. During several this life cycle analysis that we discussed in the past, we talked about this polymer quite often, okay, and much of the material I am going to talk about in this lecture are taken from this review article. So, if you want more information, you can visit this. So, the way that I want to construct this lecture is to give a very broad overview of what it takes to make PLA polymer, what are the challenges, what are the chemistry involved. That is the part of this lecture. Subsequently, we will talk about various products, plastic products made up of polylactic acid, okay. So, that is the context. So, before I say anything about PLA, I just want you to remember a few things, okay. There is a molecule called lactic acid, okay. So, it has this CH3, CHOH and then COH, okay, a very simple, seemingly simple molecule, okay, lactic acid. Then two lactic acid moieties can come together and it can form something called a lactide, okay. So, lactic acid is a monomer, it is a very simple molecule, but lactide is basically formed through two dimers forming a condensation reaction like this, right. So, two lactic acid molecules come together and water is removed. So, then you get this kind of a cyclic dimer which we call as lactide, okay. And this lactide is what shown here. This end is basically the CH3 group, this end also has a CH3 group. What you can do with the lactide is you can, through some catalyst and other things, you can actually polymerize lactide into polylactide or polylactic acid, okay. So, we start from lactic acid and then build a lactide. From lactide we polymerize and get polylactide or polylactic acid. So, PLA means both polylactic acid or polylactide, okay. So, I want you to remember what is lactic acid, what is a lactide and what is polylactide or polylactic acid, okay. Those things I want you to remember. So, now let me make some remarks about what is the current status of PLA. PLA is a eco-friendly, that means it is going to be compostable, it is a thermoplastic polyester, okay. So, polyester means it will have COOR kind of a chemical group, right, and it can degrade into CO2, water and some lactic acid oligomers. So, that means that is what I am saying, it is eco-friendly because it ultimately degrades into CO2, water and some low molecular weight oligomers. There are some drawbacks of the native polylactic acid, such as they form a brittle film or brittle products and it has a very low toughness. That means it actually can absorb very little energy upon impact and then could be quite costly in comparison with other petrochemical derived plastics, okay. So, these are some of the existing drawbacks with respect to PLA. Over the last couple of decades, a lot of studies have been done on PLA with regard to what are the mechanical properties, what are the crystalline nature, the thermal properties like glass transition temperature, melting temperature, the degradation standards, compostability, aging effects, and then to what extent you can recycle. A lot of work has been already done on this particular polymer. Now, apart from native or the virgin PLA, there are also composites. Generally, PLA is used as a matrix with which you can add some other fillers, additives to reinforce the polymer. Okay, just like for example, if you consider nylon, you could mix glass fibers, you can add silica, you can add carbon black to reinforce the property. Same way with the PLA also, one can think of adding additives as a reinforcement agents. Now, PLA seem to have a very large range of applications, including food packaging, agricultural mulch forms, mulch films, automotive products, lot of additive manufacturing like 3D printing applications, printed electronics, tissue engineering, and so on. Another one area that is upcoming for PLA is to make a PLA PLGA copolymer. Okay, and this PLGA is biocompatible biocompatible, so that you can actually use it in pharmaceutical field also. Okay, it's an upcoming area. Based on all these things, now it is understood that PLA is a commercial biopolymer. What we mean by commercial? It means it is produced in such a large quantity that it is available for various kinds of uses. We say polyethylene is a commercial polymer. We say polyvinyl chloride (PVC) is a commercial product, because with polyethylene or PVC, you can produce in large quantity, cheap cost, low cost, and then also you can make all kinds of products with that. Okay, and PLA has actually attained that status in terms of production, the areas of application and so on. For example, over the last 10 years or so, from 2011 to 2020, the production rate has been reported to be about 4-fold increase, going from 200 kiloton to 800 kiloton over this 10 years. And I think what is the next thing to do would be to increase the production rate of PLA, so that you can penetrate into many other fields, and also try to replace the existing plastics which are based on fossil fuel based. Okay, so these are some of the initial remarks I want to make. Now, in the first slide I talked about lactic acid and then lactide. Okay, lactic acid is a monomer, lactide is a dimer. Okay, and polylactic acid is a polymerized version of a polylactic acid. Now, if you look at the production of PLA, you can actually use lactic acid and lactide as a precursor, that we have to remember, because I am going to take some more inputs from here. And if you think about how we do polymerization, there are two kinds of polymerization. One is called this direct polymerization. That means you take your monomer, which is polylactic acid, okay, and then directly do a what's called a condensation reaction, with which you can create a polylactic acid. So the direct polymerization uses lactic acid, whereas another polymerization, which is called the ring opening polymerization, uses lactide, because as I said, lactide is a cyclic molecule. It has this ring like structure. So you open that ring, that's why it's called ring opening polymerization, and then you add you basically continue to add and then form polylactic acid. So the point is, polylactic acid can be made in two routes. One is direct polymerization using lactic acid monomer, or ring opening polymerization using dimeric polylactide. Okay, I will also talk about what are the issues with the direct polymerization later on. Well, that's right here. So when you think about this, when you take lactic acid, when you try to directly make into polylactic acid, you will see because of this condensation reaction, a lot of water will come out. Okay, so that means you have to manage this water that is getting released. So this means that you have to increase the temperature so that you can vaporize all the water that is formed, or you have to find some other mechanism with which you can remove water. Okay, so this leads to a lot of issues. For example, it actually interferes with the reaction, and because of that, you cannot achieve a very high molecular weight PLA if you want to do direct polymerization. From a chemistry standpoint of view, it is very easy. You take polylactic acid, put some catalyst and directly polymerize it. Okay, but because of the production of water and removal of water, and the reaction condition gets affected, you cannot build a very high molecular weight polymer. Okay, as far as you are interested in the low molecular weight PLA, direct polymerization is okay. But if you try to use the dimer, which is lactide, you're going to do what is called ring opening, and that does not involve this water production. So, here you can actually go to very high quality PLA, at the same time very high molecular weight, right. And if you think about the yield, suppose if you take about 10 million tons of food waste, first from the food waste you will create lactic acid, okay, it is about 2.5. So, 4 times lesser amount of lactic acid is produced. From lactic acid about 1.7 million ton is produced in terms of lactate. That means all lactic acid is not going to lactate formation, and similarly when you go from lactate to polylactide, you see another reduction, okay. So, that means with respect to the raw material, you are basically like 1:10 ratio of polylactic that you can produce. So, what that means is in each step when you go from your food waste to lactic acid, and from lactic acid to lactide, and from lactide to polylactide, there is always an issue of selectivity, yield, purity, all that. So, therefore, a lot of research or innovation is needed to find a preparation method and purification method for lactic acid and lactide throughout the entire PLA industry, okay. So, that is that's what drives more research on this particular field. I will not be talking about all the chemical details, but I will just touch upon few important terminologies, and if you are interested we can look at these details later. So, one more thing we have to remember is this lactic acid that I talked about is actually a chiral molecule, okay. It actually forms D type and L type polylactic acid, and here in this table we are comparing various physical properties between the LLA and DLA, okay, the left handed and right handed lactic acid. This racemic mixture means some proportion of both L and D are formed together, okay. So, if you look at the melting point between LLA and DLA, they are not very different. Boiling point is also very same, appearance also quite same. There is a small difference in the density, as you can see, and various other things are very similar. However, the activity of these molecules in the human body or human consumption, there is a huge difference between LA and DLA, okay. For example, the DLA and racemic mixture are actually harmful for the body. So, the hope is to get, suppose if you want to use biological application of PLA, you should be having high purity left handed LA and then the polymer made from LLA, okay. So, what happens is that when you try to, I'll talk about the synthetic methods. The real challenge is how to increase the production of stereoselective or L rich lactic acid in high quality and high quantity, okay. But often you will see that you will form both LLA and DLA, and the separation of that becomes a big issue, okay. So, that is a real challenge. So, now I will talk about how to synthesize lactic acid. There are two routes. One is the chemical synthesis, the other is biosynthesis. In the biosynthesis, we will be using agricultural products, but in the chemical synthesis, we start with some known chemical compounds. For example, in the chemical synthesis of lactic acid, you could start with a glycerol, okay. So, the CH2OH, CHOH, CHOH, and here the first thing is to do some sort of a dehydrogenation. Most of them are catalytic, high temperature, high pressure, okay. So, when you try to extract hydrogen from here, you get what is called this glyceraldehyde, and then you extract water away from this, you get something called pyruvaldehyde, and then you remove one more OH, you get this lactic ion, which is called lactate, and the selectivity here is only 63%. That means, if I take 1 mole of glycerol, I am going to get only 0.63 moles of lactic acid. What happens to the rest? Well, there are a lot of side reactions. Things do not happen in this particular expected way. You can see that sometimes the glycerol can actually undergo some sort of a carbon-carbon breakage. You can end up making ethanol and methanol. That is not your desired product, okay. So, if you do not control your reaction, or if you do not have a proper catalyst, you cannot prevent this side reactions. Or from this step, you could actually form something called glycols, okay. Instead of going this direction, some amount of reaction will also happen to this way. So, in the chemical synthesis, the real challenge is the selectivity, okay. So, you get a lot of the side products, and because of that the production of lactic acid is compromised. So that's why, because of this reason, among the overall lactic acid production, only about 10% is actually chemically synthesized. The remaining 90% are synthesized biologically or using biosynthesis. Another thing you see here is that these reaction mechanisms are quite complex. It involves many side reactions, and it uses a lot of resources and energy and waste because of other unwanted chemicals. And it also, we are not able to control the production of different chiral isomers in this particular step. Okay, you will get both LLA and DLA. So we don't have a good control on controlling the selectivity of these molecules. Okay, so these are the challenges of the existing chemical synthetic route. So then we go to what is called this biosynthetic or biosynthesis of PLA. So here the idea is to take carbohydrates from various I think I have let's say corn, or it could be agricultural waste like rice husk and other things. Okay, so whichever carbon rich resource that is available in large quantity, low cost, you can take that as a carbohydrate source, and you try to convert this carbohydrate into sugars. Okay, and this process typically involves treating carbohydrate with with an acid mixture, so that you can break open the structure and release glucose molecules. And after that, once you have sugar or glucose, you do what is called fermentation using microorganism. You use some biochemical pathways to convert the sugar into a lactic acid. Okay, so previously we saw a chemical synthesis. We take a raw material like glycerol and convert into lactic acid. Okay, here in biosynthesis, we take sugar, we make use of microbial systems to convert the sugar into lactic acid. Okay, then what happens is that you get a fermentation froth, which will have all kinds of things. There will be cells, there will be protein, there will be lactic acid, there will be salt, there is going to be whole lot of other things. Okay, and how are we going to purify those things are the very critical steps. Typically chromatography columns, ion exchange, precipitation, distillation, many other things are used for purifying lactic acid. And finally, as I said, if you want to do direct polymerization, you can do polycondensation reaction to get PLA, right? And the typical bacterium that is used is this Lactobacillus rhamnosus. There are many varieties of this, many strains. Some are engineered to increase the production rate of lactic acid from sugar. Okay, so what we are saying is, we look at carbohydrate sources and we try to convert this carbohydrate into sugar, doing some chemical treatment, take this sugar as a substrate, feed it to microorganisms like bacteria, right, and use their biochemical pathways to convert sugar into lactic acid, and then extract the lactic acid and then polymerize it. That's the way that it works in the case of biosynthesis. Some more information about I want to say, I already mentioned corn, but also corn, rice, sweet potato, lot of starches is possible. Recently, there is also interest in using waste material, because the first line, it talks about food consumption. Like, I mean, if you're going to use a lot of food material, it's going to affect the food security. So, there's a lot of attention being done in towards using non-food based or food waste or agro waste based raw materials, that is involving kitchen waste, lignocellulose and other things. So, I already mentioned about the microorganisms and how the LA is produced. The fermentation itself actually involves two kinds of approaches. One is called this homolactic fermentation and heterolactic fermentation. What it means is, in the homolactic, each glucose molecule can give you 2 lactic acid theoretically, in theory, okay, but in practice that's not going to be the case. Whereas in the heterolactic acid, what happens is, one glucose will give 1 lactic acid, and there's going to be some other products like ethyl alcohol, acetic acid and other things. Okay, so depending upon which microorganism you are going to use, the fermentation mechanism can be either homolactic or it can be heterolactic. So as I said, the once you produce this lactic acid in the fermentation cell, you're going to have pigments, cells, proteins, salt, various kinds of other things. So purifying your lactic acid from this fermentation broth is very challenging, and often it is said 50 to 60% of the cost in the entire production of PLA goes into this particular fermentation separation. Okay, so as I said before, chromatography, membrane separation, extraction, adsorption, distillation. If you're a chemical engineer, you should be happy about seeing these terminologies. Okay, so you can use all the kind of mass transfer operation that you learn in chemical engineering and try to use here to separate lactic acid. Now, the advantage of this biosynthesis is that because we are using bacteria or microorganisms, the stereoselectivity is quite high. Okay, so the bacterium will actually selectively produce only L type La, which is what we want. Okay, whereas in the chemical method, that selectivity is not there. So that's why 90% of the lactic acid production is through bio. Now coming to lactate, so lactate, as I said, it's a 6-membered cyclic dimer of lactic acid, and it is a key intermediate for the synthesis of high molecular weight La. This already mentioned. Like it's important to note this LLT and DLT. So what this means is, this is left-handed lactite, this is right-handed lactite. When you create a polylactic acid from this L type or D type, the mechanical property can be quite different. Okay, so for example, the L type polylactic acid is actually completely, it actually can be degraded to LLA, and it can also be metabolized by human body, but not the PDLA. Okay, so it is important to do high purity of LLA for producing the polylactic acid. So here again I am comparing the L type and D type lactite, which is this, and you can see that in terms of physical property, mechanical property, they are very similar. But then when it comes to bioavailability or biocompatibility, there is a huge difference between L type and D type. And how do we synthesize lactate? I already mentioned lactate is nothing but a dimerized form of lactic acid. Okay, so this can be done in 3 different ways. There is a 2-step synthesis, there is a gas phase synthesis, and there is a 1-step synthesis. Okay, these are the types in which 2 lactic acid molecules are combined together to form a lactate. Okay, so let's look at each one of them. I'm not going to discuss the details of the catalyst and conditions, but I'll try to say as much information as needed for you. For example, if you consider 2-step synthesis, you start with your lactic acid, okay, and you do what is called this polycondensation. You will actually create what is called this low molar mass PLA, okay, low molecular weight PLA, and some amount of water will come. Okay, if you continue this reaction for long, because of the production of water, you will have some sort of a limitation in how much you can grow. Okay, so that's the limitation I already mentioned about direct polymerization. But in this case, we want to only make a dimer, not a polymer. But this kind of polycondensation will give you low molecular weight PLA, and what you do is you take that and then you do something called a depolymerization. You depolymerize this back into lactite. Okay, so you start with the monomer, you build a very short chain polymers, and then you break this polymers or you depolymerize this to a lactite. Okay, so that is your end product, and this is what we call 2-step process, because in the first step we do polymerization to low molecular weight polymer. In the second step we depolymerize that into a lactate. Okay, the second is what is called this gas phase synthesis. In the gas phase synthesis, we try to what we try to do here is you take a renewable carbohydrate, ferment it, you get left-handed La, and here we try to esterifize this lactic acid with methanol. We add methanol and we create methylated La, and this methylated La is sent through a packet bed, a reactive packet bed, in which you choose a particular catalyst that will specifically form a dimer only. Okay, that means you are going to make only L type lactite. The way it works is, you can see there is a packet column, this is a reactor containing a catalyst. You would send your lactic acid from a fermentation reaction at the top, and then also you will add methanol from here, and it is combined to form a MLA. MLA is nothing but methylated lactic acid, and that passes through this column. Okay, and then this reaction happens where the lactate is formed, and then it is sent through a distillation column where you separate lactite from methanol, and methanol is recycled back. Okay, this entire operation is done in a gas phase. Okay, so that's why it's called gas phase. And here you can see that the lactide selectivity can be 90%. Okay, that means this catalyst is so specific, it will only form dimer and not other kind of trimer or tetramer. Okay, so it's very highly selective. So this is second method. So first method is two-step synthesis. We take lactic acid, make a small sized polymers, and then try to depolymerize it and then get lactate. This will have issues with selectivity. You will not be able to exactly get lactate. There's going to be always lactic acid and higher molecular weight. Then you have to again worry about purification. Okay, whereas in the gas phase synthesis is very selective, and it involves taking lactic acid, reacting with methanol, and get a methylated lactic acid. Then catalytically you convert that into a lactic acid. Sorry, lactide. So that is the method of making this gas phase synthesis. The third approach is what is called this one-step synthesis. In the one-step synthesis, what we try to do is we use some sort of again a zeolite kind of a catalyst. You start with a monomeric lactic acid. It is done in a liquid system. Okay, use a catalyst, and ideally you want to make a dimer, which we call this L2A, that is a lactide. But generally, the reaction is not exactly controlled. You'll have some sort of trimer and tetramer also, right? And then once you have it, then you have a system of separation. You do what is called this liquid phase separation or extraction. Remove the solvent and use the solvent back, and then you have another method in which you kind of separate the unreacted or unreacted lactic acid. So three methods to produce lactide. One is a two-step method, then you have a gas phase, and the one-step liquid phase method. Okay, so these are the three different things with which we can create lactide from lactic acid. So here I think it's the different things are compared here: two-step method, gas phase method, one-step method. You can see that in the two-step method, the temperatures are about 130 to 180. The gas phase method operates high temperature because you do everything in a gas phase. One-step method, it's a liquid phase method, so it's usually a low temperature method. And you can see the yield is also reported here. Now, so we talked about lactic acid and then lactide. Now we're going to talk about polylactic acid. Okay, so as I said, that this polylactic acid or polylactide is a linear aliphatic polyester, right? And so there are two methods of polymerization. One is called this polycondensation, other one is called the ring opening polymerization. But if you look at the polycondensation itself, there are again various types. One is this direct polycondensation, where you just link the lactic acid and you do what is called polycondensation. Then there is something called azeotropic dehydration based polycondensation. There are second order melt polycondensation, third order solid state polycondensation. I am just only naming these things because if you look at each one of them, it requires a very complicated set of processes and catalysts and conditions. So that is not the scope of this course. If you're really interested to know what these, if you're a chemist, for example, okay, and there's a lot of scope for coming with new kind of catalyst to improve the purity, the stereochemistry, the stereospecific purity, and yield, all that is possible if you go to any of these chemistries. The polycondensation involves only lactic acid, whereas the ring opening involves a lactide, which is the dimer. Again, the ring opening can be done through various mechanisms. You can use a metal catalyst, you can do a cationic or anionic, organic, enzymatic ring opening mechanisms. Okay, the ring opening can be done through many different ways, and these are all the different pathways. Again, a lot of chemistry is involved in this case, different catalysts are involved. So I will leave it to you to read more about these polymerizations if you are interested. Okay, so I just want to only state that it is not just one polymerization. There is a whole lot of variety of polymerization that is done. So here is a kind of comparison between polycondensation and ring opening. So you can see that typically the ring opening, which uses the lactide, right, the dimer, it can reach about 10 power 5 molecular weight, whereas the direct polymerization can go up to 10,000s. At least that's a 1 or 2 orders of magnitude difference. And like I said, in the case of polycondensation, production of water is very difficult to change, and because of that the molecular weight is low. And in the other cases like azeotropic or second order, there are few other requirements required, and whereas the ring opening seems to be the one that gives you high purity lactide, and also it requires complex processes and high costs. Okay, so this just I want to mention. Apart from the lactic acid, lactide, from there to polylactic acid, many times we also do what is called copolymerization. Okay, polylactic acid is actually copolymerized with other kinds of polymers too. I have given some 3 examples, but there are many. For example, you take the lactide as one monomer, and another one as this polypropylene glycol didecyl ether is another monomer, and then you polymerize these 2 monomer, then you get a polymer that is called this polypropylene glycol glycidyl polyether. Okay, this is based on again a ring opening mechanism. Anytime you work with the lactide, it has to be a ring opening polymerization. And another example is you take a lactide and then use a glycolid, and then again put some catalyst and base, and then you can create what is called this polyglycolid, polylactic acid, polylactide, polyglycolide tri-block copolymer. Okay, so it's basically repeating units of 3 blocks of polyglycolide, polylactide, and then polyglycolide again. Okay, so these kind of polymers are shown to have very high tensile strength, elastic modulus, highly thermal stable, and then it has a wider range of thermal conditions so that you can do extrusion, blow molding and other things. Okay, so this kind of copolymerization is typically done to improve glass transition, thermal stability, increase the strength, tensile strength, hydrophobicity and other things. And the last one I want to highlight here is polylactide, polyethylene glycol polylactide. If at all you want to increase more flexibility, I said PLA is very brittle polymer, but if you co-polymerize with this polyethylene glycol, you can make it a little bit more flexible. Okay, so here is only few examples, but you can think of many other monomers. As long as they are also biodegradable or biocompostable, you should be able to link with it and try to change the properties. And blending. So many times so block copolymerization means chemically you are linking the polylactic acid in the backbone so that you build a copolymer. What is other possibility is that you can also mix or blend PLA polymer with other polymers too. For example, in the literature you will see PLA mixed with a starch in different proportion, and starch can be from a different composition. We already saw starch means mixture of what? Starch. You just wanted me to just keep talking, right? Huh? Amylose and amylopectin, and depending upon the source of starch, you have a different fractions of amylose and amylopectin. So that means starch is not just one single compound, it will have a lot of variability from their source and the relative amounts of amylose, amylopectin, right? And then when you mix with the PLA and starch, you can again create new kind of blends that would serve your purpose. And lignin is also another. What is lignin? Where is lignin coming from? What is lignin? Where did we see lignin previously? Huh? Cellulose is not lignin. It's a kind of. Where did we find that? Where did we? We saw in wood, bagasse, right? In many of these biomaterial, it's composed of cellulose, hemicellulose, lignin, and lignin chemically how do they look like lignin? Do they contain sugar molecules, sugar structure? No. What do they have? They have aromatic rings with a lot of polyols, right? Okay. So you can also mix lignin with the PLA, again improve their property. Cellulose, we already talked about cellulose, various kinds of cellulose, right? And there is another kind of polymer I will talk about in few next in another few classes or so from now. This polyhydroxyalkonates is also a very important biopolymer, microbially synthesized, that can also be mixed with the PLA to make PLA PHA composites, right? And another range of possibility is there are a lot of polysaccharides that are extracted from seaweeds and various other microbial sources. So mixing with the alginate, chitosan, gelatin is also possible. Okay, so gelatin is a kind of a protein, right? You can mix protein with PLA and make new material. Okay, so basically the number of possibilities of mixing PLA with so many other biomaterial or bioequivalent material is quite large. Okay, so this is again an expanding range of activity that is happening. So so I think that's all I have, and I will talk about PLA's mechanical property, what are the thermoprocessing operations, what are the products that are made with the PLA in subsequent classes, right? So any questions at this point? Okay, so as I said, please take a look at this particular journal. This is 2023 journal. It gives a lot of this is a chemical reaction I was talking about, right? Polymerization, a lot of chemistry details are there. If you are a biotechnologist, you have a huge opportunity to work on this PLA system, because finding the right fermentation process and separation process is highly needed. If you are a chemist, then you also have a lot of potential, because this ring opening polymerization requires a lot of catalyst expertise, okay, to be able to generate or produce L specific lactic acid through your chemistry. Okay, so even though the last 20-30 years a lot of work has been done on PLA, but still there is a lot more opportunities to work from a biotechnology point of view as well as from a chemistry point of view. And chemical engineers don't lose heart. You also have a lot of opportunity, because in terms of separation of the lactic acid from the fermentation, again, so it's a kind of an interdisciplinary approach. All of us have to work together to find a microorganism that can effectively convert sugar into a high purity stereo purified lactic acid, and how do we optimize that process for higher yield. That's one. The second is how do we separate effectively. Low cost separation technology is also needed. The third, how are we going to come up with a new kind of catalyst, low cost catalyst, highly selective catalyst to convert lactide into polylactic acid. So all three are existing challenges. Okay, this problem is not solved yet. Okay, so there's a lot of potential to work on this particular area. Okay, that's all for now. Thank you.